Hello and welcome to Chandler Science AP Physics 1 Dynamics Problems. In today's lesson, we're going to look at the differences between static and kinetic friction, and then we're going to take all the knowledge we've gained so far from videos and in class and everywhere else and put it to use and do some practice problems with forces at angles and then on an inclined plane. So we should do 2 to 3 example problems today. We'll save the tension, pulleys, springs, all that stuff for a different video. I don't want this video running 30 minutes plus, so try to keep it a little bit shorter. Alright, so if you're one of my students or in my class, make sure you're taking notes and you're going to ask one question at least on the discussion forums and then respond to at least one question on the discussion forums as well. If you're from somewhere else on the internet, welcome. I hope you enjoy and hope you find these example problems useful. Let's get started. Alright, so let's talk about friction. We've seen this equation already in class several times. This is friction force less than or equal to mu, that's the Greek symbol, or Greek letter mu, stands for coefficient of friction, and then times the normal force, that's Fn, right? And the reason why there's a less than or equal to sign will become clear in just a minute. Let's talk about the 2 different types of frictions, static and kinetic. So first let's talk about static friction. This is the friction you experience when an object is at rest on a surface, and it's the force you have to overcome to get it going, right? If you ever push like a large heavy box, it doesn't have to be a large heavy thing, but it's kind of more noticeable when you're pushing a heavier object. You're pushing a really heavy object and it just won't budge for a while. You're pushing it, right? You're applying a force, but it's not moving, right? But then eventually, if you push hard enough, boom, it starts to move, right? Get that sudden jolt, you know, and then it's a little bit easier to push. Once it's moving, it's actually easier to keep pushing it. Okay, this is because static friction, the coefficient of static frictions are always greater than the coefficient of kinetic friction. Okay, so why is it less than or equal to? Imagine you have a box, right? And let's say this box has a weight of, let's say it's a weight of 10 to 100 newtons. And then let's say it's on flat ground, so its normal force will be equal to the 100 newtons, right? So, because we're not going to push it down or anything. And let's say the coefficient of static friction, let's say is 0.8, it's pretty high, right? Well, if the normal force is 100 and mu is 0.8, that means our friction force for static, and a little s there for static friction, so 2 subscripts, a little f and then a little s for static friction, is going to be 80, right? 80 newtons. Now, I see I messed up. I shouldn't have put an equal sign there. It's less than or equal to, my bad. Less than or equal to. Okay, now, so why is that the case? Let's say you want to move this box. So you come along and you push the box with a force of, 40 newtons, right? Now, the friction force is going to resist, right? Friction resists the force, so the friction force will push back now with a force of 40 newtons. It's not going to push back with all 80 because it doesn't have to. Think about what it would mean if it did push back with all 80, right? That means if I'm pushing forward on the box with 40, it's going to push back with 80, so it's going to accelerate towards me. That's really weird, right? That doesn't happen in the real life. So what happens is the friction force matches your force. Now let's say I push with 60 newtons of force. If I push with 60 newtons of force, what's the friction force going to be? The static friction force will also be 60. It's going to match it. And then I'm going to say, oh damn, I got to push a little harder. All right, so now let's try pushing at 80 newtons. And I push 80. Like, nope, less than or equal to 80. So it can push 80. All right, so still not going to budge, right? My net force is still 0. 80 to the right, 80 to the left. I'm still have no net force. I'm not accelerating yet until you overcome that friction force. And let's say you push at 81 newtons. I push 81 newtons. Well, the static friction force can only go up to 80. It can't go to 81. So what happens? You overcome the static friction force, and you get that little jolt, and then, oh, there it goes. Now it's going to start moving, right? And you get an acceleration. The moment you overcome the static friction force, it instantly changes to kinetic friction. So let's say the kinetic, so let's put a little s here for static. Let's say the kinetic friction force was, 0.6. Always going to be less than static friction. If it's 0.6, that means that the friction force will be 60, right? 60 newtons. That means my net force here in the x direction will be 81 minus 60 will be 21 newtons. If this thing had a mass of 10 kilograms, then my acceleration of this object would be net force is 21 over 10 will be 2.1 meters per second. Whoa, meters per second squared. Okay, so sometimes on problems it'll ask you, is the force that's being applied even enough to move the object at all? Is it enough to overcome the static friction? So first we got to see, okay, is the force we're applying even big enough to overcome static friction? If it is big enough to overcome that static friction, then we're like, okay, we don't need to worry about static friction then. We're pushing it hard enough to overcome it, so let's focus on kinetic friction. So what will the kinetic friction be? And then we use that one, right? We use that coefficient of friction to find the friction force. Now for friction force of kinetic, it is equal to mu times the normal force, right? So this symbol less than or equal to really only applies for static friction. For kinetic friction, it actually is just equals to, right? Which brings me to the definition of kinetic friction. This is the friction of an object while it's moving between the two objects, right? While they're rubbing against each other. And this is the force you have to kind of fight against while you're moving the object, right? So you're pushing the object one way, friction force is fighting you, and you have to kind of like, you know, at least match it if you want to keep going at a constant speed. All right, so hope that made sense. If you have any questions about what static friction or kinetic friction is, or the differences, you can ask them in the forums or shoot me a message on mine or email. Let's move on to our first kind of major problem here in the next slide. All right, here we go. First example problem, we have an object, doesn't matter what it is, and there's a force being applied to it at some angle. So let's make up some numbers here. Let's say the box has a mass of, I don't know, how about 15 kilograms. And let's say this angle of the force, the horizontal, the angle here, let's say it's, so I don't know, how about 22 degrees. Why not? And then we'll say the applied force on the object is, I don't know, how about, let's say 130 newtons. Seems fine. And we want to find the acceleration of the block, and we're going to have a coefficient of kinetic friction. Let's just assume that we've already overcome the static friction. Let's not worry about that in this problem. Let's say the kinetic friction coefficient is 0.4. All right, 0.4. There we go. Okay. All right, and like I said, we're trying to find the acceleration of the block. So I tell my students all the time, the first thing you want to do is draw a free body diagram. So that's what we're going to do. So I'm going to go down here, and I'm going to say, all right, I'm going to represent the object as a little dot and draw all the forces on the dot. So first we have gravity. We're on the Earth. So down, straight down, mg. We have the normal force, the ground itself, the surface we're on, is pushing it back up. I call that Fn for normal force. We have an applied force, so someone's pushing and pulling the box at an angle right here. I'm going to call that force applied. And then we're going to have friction force back this way, right, opposing the motion, right there. So that's our free body diagram. Now we do want to have components for that applied force, because it's not aligned to our horizontal or vertical, right? So we want to make sure to have the horizontal component. I'll do that in red, and then we want to have the vertical component, and we'll do that in blue. There we go. All right, cool. So let's go ahead and set up our problem. This is how we're doing this in my class, and most teachers and professors teach it a similar way. We want to have, first we're going to find all of our forces in the x direction, and then we're going to say also find all of our forces in the y direction, right? Add them all up. Now the good thing is we know that this box is not being lifted off the ground, and it's not being crushed into the ground, right? So we know that the sum, the net forces in the y direction, is 0. And then we're going to look at our problem and say, okay, well, what are all the forces in the y vertical plane, right? What are forces up? What are forces down? Let's call up positive, down negative. Makes sense. So we're going to say, all right, well, 0 equals this net force, the net, remember the total, all the forces added up in the vertical is 0. But what are the components, right? Let's list them individually. What are all the forces in the y direction? Well, we have upward force of the normal force, right? That's pointing up, and we also have this arrow here, the blue arrow, right? That's the vertical component of the applied force. So we're going to add that because they're both pointing up. Up's positive, so it's a force applied times the sine of 22 degrees, since that's what I said the angle was there. So those are both pointing up, and then we're going to do minus mg because mg is down, and we said down is negative, right? So I'll get my calculator over here. And again, feel free to pause the video anytime and just kind of do this on your own, and then check your work. Looks like I'm going to have the net forces in the y direction, which is 0, but then all these got to add up to 0. So the normal force, don't know what that is yet, plus the applied force sine 22. All right, the applied force was 130 times the sine of 22. Make sure you're in degree mode. I'm getting 48.7. So plus 48.7 minus the weight of the object. Well, its mass is 15 kilograms. G is 10, so 15 times 10 is 150. So I know that equals 0, so I'm going to add 150 over here. So I'm going to get 150 equals Fn plus 48.7. Subtract 48.7 over to the left-hand side here, and I'm going to get 150 minus that, and I'm going to get 101.3. So my normal force then is 101.3 newtons. Cool. All right, let's do the x direction, right? All right, what are all the forces in the x plane, right, in the horizontal direction? Well, I have the red component there, right? This red arrow here pointing to the right, and I have the friction force to the left, and that's it. So I have force applied in the x direction. That's going to be cosine of 22 degrees, right? Minus, because it's the other way, the friction force, which I don't know what that is yet, but I can find that. Now it's kind of easier in the y direction because I knew that the sum of all the y direction forces was 0, but I don't know what the sum of the forces is in the x direction. That's okay though, because I'm going to be able to find out friction force here in just a second. I'm going to use my friction force equation. This is for kinetic now. Will equal mu times the normal force. We know mu was 0.4, so it would be 0.4 times normal force 101.3, right? 101.3. That's going to equal my force of friction for kinetic. So we do the math there. And, oh, I'm running over my face. Ow, don't run over my face. So over here, force of friction kinetic. 101.3 times 0.4. Oops, I did times 0.3. My bad. 101.3 times 0.4. 40.5. I'm getting 40.5 newtons. And there's my N. There we go. Okay, 40.5 newtons. That's friction force. All right, so that's going to go in right there, right? So we're going to have the net forces in the x direction is going to be, all right, force applied times cosine 22 is 130 times the cosine of 22 degrees. That's 120.5. So 120.5 newtons minus that's 40.5 newtons. All right, and that means that the sum of my forces in the x direction is going to be, what's that, 80 newtons, right? Okay, so now we're going to use Newton's second law. Let's go up here in the top right. Acceleration in the x direction. Now this object is not accelerating in the y direction. We know that. We really only set up this thing here to help us find the normal force, right? And you might think, oh, that was easy, mister. Yeah, but I want you setting up like this anyway. It's going to reduce silly mistakes, okay? So just do it. All right, so we're not accelerating in the y direction, so I don't need to make a Newton's second law equation for the y direction, only in the x direction. That's what the little x is for. Sum of forces in the x direction over the mass. All right, so what is the sum of my forces in the x direction? Well, we found it to be 80 newtons, so it's 80 divided by the mass of the object, which is 15 kilograms. To make sure you don't do weight, right? It's mass, not weight. So 80 divided by 15 is 5.3. So my acceleration then will equal 5.3 meters per second squared. And there we go. We did it. Okay, so cool. Hope that was pretty clear. Let's move on to the next problem. And the next problem will be on an inclined plane. It gets a little bit more challenging, but not too bad. So let's take a look at that one now. All right, so let's take a look at an inclined plane problem. Here we have an object resting on a ramp or inclined plane. Has a mass of 15 kilograms. We have two coefficients of friction this time. We have a static coefficient, 0.7, and the kinetic coefficient, which is 0.5. And it's sitting on this ramp, which has an angle of 30 degrees to the horizontal. And we're actually going to push the ramp. We're going to apply a force up the ramp of 200 newtons to see if we can push it up the ramp. And we want to find out what the acceleration of the object is. So let's see what we got. Now, keep in mind that whenever you are on a ramp or an inclined plane, right, we're going to tilt our axes, right? And normally, when we're on flat ground, our vertical axis is straight up in the air, right? That's y. And then our horizontal is horizontal, right? Flat. That's our x. But whenever we're on an inclined plane, right, we're going to tilt everything. We're going to imagine our perspective is that of the box or the object. So we're going to kind of go like this, and now everything is tilted. So now our x-axis is actually going to be parallel to the surface. That's our x. And then our y-axis is actually perpendicular to the surface, like so, right? So all of our vector arrows in our free body diagram need to align to our new axes, right? Perpendicular to the surface and parallel to the surface we're on. If any vector arrows don't align to those directions, we must make their components, right? So we'll see which ones we got to do that for. First step is always to draw a free body diagram, so let's do that. Make a little dot to represent my object. Straight down for weight, and that's mg. Perpendicular to the surface, force normal. Parallel up the ramp, force applied. And then I'm going to have a force. Now I'm actually going to have two forces here down the ramp. I'm going to have a component, okay, of the weight force down the ramp. I'm going to do it in blue. And I'm also going to have a friction force down the ramp also. You know what? I'm going to draw it just because I can't do this on this drawing pad. I'm going to draw it like this. Although please note that I'm going to call this friction force here. Please note that in reality, this arrow friction force should be coming out of the object. I'm just drawing it like this to make it easier to see, but it should be coming out of that object, right? But just make it easier for us, our eyeballs here. Okay. And I'm going to draw the horizontal component, or the vertical component, excuse me, in orange. It goes down like this, right? So because the gravitational force, the weight force, is, this way, it doesn't align to our new axes, right? Now our y-axis, our vertical, is now tilted like this, and our x-axis is parallel to the surface. Well, the gravitational force is in neither of those two directions, so we must draw its components. However, the applied force, the normal force, and the friction force are all either in the x direction or in the y direction, so they're good. We don't need components for them, only for the gravitational force, right? Okay, so now that we set this up, let's go ahead and take a look at our Newton's second law in each direction, right? We're going to set up an equation. Let's do sigma, net forces in the x direction, and then we'll do net forces in the y direction. Let's do y first. That's usually the easier one to do. We know, again, this object is not being lifted off the ground and it's not being crushed into the ground, so the net force on the object in the y direction is 0. But what are the constituent parts that make up that force, right? We know it's 0, but what are all the different forces in the y direction that add up to 0? Well, we look at our free body diagram, and we see there are only two arrows that are pointing either in the upward y direction or the downward y direction, right? Remember, perpendicular to the surface. And that's going to be normal force, and that's up, so let's call that positive. So force normal minus this component of the gravitational force, right? Now this component here, the one straight down, right here, this guy, that's 150 newtons, right? That's straight down. Now, I always tell my students in my class that weight force, the one straight down, it's like I tell my students jokingly that you're gonna use that number like you would use like some guy to go on a date, right? Oh yeah, buy me drinks, buy me dinner, ha ha ha, thanks for the date, thanks for a good time. Now, once you use him to find out the two components, you're like, see you later, bye, thanks for all the nice time, see you later, right? Okay, now, I'm not speaking from personal experience. I've never had that happen to me ever in my life. Please, like, come on. Obviously, that wouldn't happen to me ever. Okay, I'm mostly kidding. Let's move on. But anyway, so my point is that you use that number, 150 newtons, to find the components. And once you find the components, you don't need that number anymore, right? It's the only purpose of that number is to help us find that parallel component in the x direction and the perpendicular component in the y direction. And once we find those, we're like, thanks, buddy, don't need you anymore, and you can leave it alone, right? So anyway, now we're looking at the y direction, right? We're trying to find this orange vector arrow. Remember, I draw this arrow this way on purpose. Down, I call this the blue one down the ramp and the orange one into the ramp. If you always draw your arrows in that way, you'll always know that this angle here is always going to match the angle here on the ramp, right? So that means this angle here is 30 degrees. And I don't want to get into the geometry of how I know that. I mean, you can probably figure it out on your own if you take the time to do it, but just know that it's 30 degrees, okay? This bottom angle, right? The one kind of on the bottom of the triangle that we make, all right? So if you make sure you always draw your arrows in the same way I do. Down the ramp, right? And then into the ramp. and then you'll always know that the angle there matches the one on the ramp. Okay. All right, so let's take a look here. Well, we're trying to find that orange component, right? The other vertical component, the y direction component. So it's going to be 150 times the cosine of 30 degrees then, right? We know that must equal 0. Now, why cosine? Well, remember, SOHCAHTOA, right? Cosine is for the adjacent side. Now, it is a little weird here because most of the time, up until now, we've always used cosine to find the x component of a thing, and then the sine to find the y component. But now we're flipping it, okay? So don't want to freak you out. Just be careful in the future. Don't always assume that the sine trig function is for the y component and that the cosine is for x. Just be careful. Look at your triangle and say, okay, well, this is adjacent, so I need to use cosine. And it just so happens that this orange vector arrow here is in the y direction now. So cosine is for y in these types of problems. All right, so 150 cosine 30 is, I think, 120. But I'll double check. Yep, 129.9, so 130 looks good. So it's f of n, minus 130 equals 0. So I'm going to add the 130 over to that side. So Fn equals a positive 130 newtons. So cool, I'm going to label that now, 130 newtons there. All right, excellent. So now I know all my vector components in the y direction. Let's go to my x direction and take a look. So what are all the arrows in the x direction that's parallel to the surface? Let's call up the ramp positive. So I have only one arrow in that direction. That's the applied force, which is 200 newtons. And then I'm going to have down the ramp, I'm going to have the blue component of the weight force, right? And so this time I'm going to use 150 sine of 30, right? Because that's going to be opposite the angle, right? Opposite side of the triangle, so that's sine, so 150 sine 30, minus the friction force. Now let's see. Let's see what static friction is. Is this object even going to move at all? All right, are we pushing hard enough to get it to move, or is it going to match our force and not let us move? Okay, let's find out. Let's see here. All right, so first we got to find out the friction force for static will be less than or equal to the coefficient of static friction, which is 0.7, times the normal force, which now we know to be 130 newtons. So friction force for static will be less than or equal to 0.7 times 130. I believe is 91. So 91 newtons. So the maximum amount, right? The max amount that this force of friction static can apply is 91 newtons. So let's see if we're going to beat that. Now we also have the weight force down the ramp. So our upward force of 200 has to beat the friction force, and it's got to overcome the static friction force and overcome the weight force. Now the weight force here is going to be 150 sine 30. It's going to be 75. So 200 minus 75 minus 91. Are we pushing this object? Are we even going to get it to move at all? Is it going to accelerate at all, or is it just going to kind of I can't push it, it's too heavy? All right, well, 75 or 200 minus 75 minus 91 is 34 newtons. So we are good. We are going to accelerate this box up the ramp. Yay, we did it. Now here's a trick, guys. Be careful. Now that we know that we are going to push the box up the ramp, this is not the net force, right? We were just testing to see, are we going to be able to even get the box moving at all? Are we pushing hard enough to overcome that static friction? Now that we know the answer is yes, because this number is positive, right? We have a net force up the ramp, even with the maximum amount of static friction force. That means we need to switch from static friction to kinetic friction. So this number here is going to change. So I'm going to erase 91. 75 stays. I'm going to erase this guy. Now, what's the friction force for kinetic friction? Now that we know the box is moving up the ramp. All right, let's go over here. So friction force for kinetic now will equal the kinetic coefficient of friction, which is 0.5 times 130. That's going to be 65 newtons. So now instead of minus 91 is minus 65. So now that the box is actually moving, and again, we had the weight force down the ramp at 75. That didn't change. So 200 minus 75 minus 65. So now our net force is actually 60 newtons, right, in the x direction. All right, so we are going to push the box up the ramp. What's the acceleration of the ramp? Well, We'll go over here. It can be no acceleration. We know there is no acceleration in the y direction because the net force in the y direction is 0. But what about in the x direction? So the net force in the x direction, x, put a little x's there just to remind myself that I'm looking for the acceleration in that plane. So my acceleration will be, we just said it was 60, right? So 60 over the mass, which is 15. And my acceleration in the x direction will be a positive 4. Oh, I need that. 4 meters per second squared up the ramp, right? We did it. All right, we're pushing the box up the ramp. Okay, a lot to take in there. So we've gone over the 20-minute mark here. Don't want it to go too long, so I'm going to leave you with one more problem. If any of this was confusing, and I know it's a lot of different steps, but I think if you follow this process of first thing, always drawing a free body diagram, that's always step 1. Step 2, breaking it down into all the horizontal forces and all the vertical forces, and then seeing what your net forces are. Finding your net force is very important, and then using Newton's second law over here to find the acceleration. Follow those steps, I think you're going to be okay. Oops, let me make that a step 4, I guess, right? I'm messing up my things. Step 4, there we go. 1, 2, 3, 4. Hopefully that works. If you have any questions at all, email me, message me on Remind, post the questions to the discussion forums if you're one of my students, and ask me questions anytime, because I don't have a life and you are my life. So make sure you guys take advantage of my expertise. Okay. Before I go, I want to leave you with a challenge problem. Here we have an object that is not only on an inclined plane, but the applied force itself is kind of at a weird angle, right? So if you want, I'll give you some numbers here. Let's say this box is 10 kilograms, and this applied force is at an angle to the surface, right? This angle here, let's say it's, I don't know, how about 15 degrees? And let's say it's pushing up, this force is pushing up with about, I don't know, how about 200 newtons. Okay, and then you tell me whether or not, I'll give you coefficient of friction. You can make them up on your own if you want to, but I'll give you some. Let's just say kinetic. Let's not worry about static. Let's say kinetic friction is 0.5. Okay, and so I want you to find the acceleration of the block up the ramp. Right? What's the acceleration of the block up the ramp? I think that's everything you need, right? Force, angle, mass, kinetic friction. That should do it. All right, so give this one a shot. It's the exact same steps we just did, only you're going to have to find a few more extra components along the way. All right, so give that a shot. Do that on paper. Show all your steps. Show me in class, and we'll talk about it and go over it, and give you some extra credit if you get it right. Okay, so again, I have no life, you're my life, so message me, email me, all that stuff. Hope you had a good time. Hope you learned something, and I'll see you later.